Okay, so what we have here is we have a dyno chassis, and the RC car sits on this long black flywheel, okay, right here, and it is the whole entire back end of the chassis. So both wheels are basically touching it, and as I spin the wheels, it spins this long black flywheel. And that's attached to this gear at the bottom here, and also there's a belt that runs to this top gear, and these are both the same size gears. And then this one inside, okay, or this one right here, this gear is then attached to the flywheel that's inside this housing. Okay, this one is red, you can kind of see it, it's aluminum. Okay, and it's spinning that flywheel. Here is a steel one. All right, and on the flywheel it'll have these white and black sections. And we can use a phototransistor, a reflective object sensor. It can actually be used to determine when it's actually in the white section or the black section. Okay, that's why they have these white and black sections. It's really cool, and it reads it really fast. It'll read voltage. So it'll read, depending on your light intensity, in my case, it'll read like around 2 volts, and I'll show you that. As soon as it hits a black, this sensor will shoot up to over 4 volts. So as this thing spins, all right, we can read what they call spikes. It'll shoot up and then back down, shoot up, back down, shoot back, and then we can use that data to calculate revolutions per minute. And basically what I did is over on here on the right, I basically 3D printed a holder to hold this on. So let me move this over. Okay. Boom. And this sensor is basically millimeters away from the flywheel, and there in the data sheet it'll tell you how far away it should be. Okay, so I just hot glued it in there, and then over here is the circuit, a couple of resistors, some wires to get this thing powered by this device here, and to read the signals coming from it. Okay, to read the voltage between the white and the black as it approaches. All right. So I'm not using Arduino. I'm using a National Instruments data acquisition card. It's a NI USB 6008. I'm using what they call MATLAB, not C++, and because I'm more familiar with that. And then that just runs to the computer, and I can do the analysis on that. So this is the first step, is try to get the sensor working to read the revolutions per minute. And then the next step would be to try to do the motor and control the motor. And then I'm going to wait for a few seconds, and then I'm just going to hit the throttle. I'm just going to pull this down. Okay. All right, should be good now. Pulling it down. After running the experiment, all right, for 20 seconds, I increased the throttle on the transmitter. We got these spikes, all right? So as the sensor goes from white to black, white to black, white to black, okay? And these spikes, okay, are down here at about 2.2 volts when it's in the white, and then it shoots up over 4 when it's in the black. And if you notice, the gap between these spikes gets smaller and smaller as you move to the right, because I'm increasing the throttle, I'm increasing RPMs. Okay. So again, this is coming from the Phototransistor. Okay, here's the data sheet. It's a reflective object sensor. Okay, and the schematic and how to hook it up is inside here. What we can do is we can take that data set and I can run calculations on it over a period of time, and I can calculate a bunch of things. But I found out how to calculate revolutions per minute. So here's revolutions per minute as a function of time. All right, as I increased the throttle, the RPMs increased, and it reached about 2750, roughly between 8 to 20 seconds. Then I can actually calculate what the speed of this RC car would be based on the circumference of the tires, and it peaked out around 12 meters per second. Okay, so this is great. I'm one step closer to figuring out, like I understand now how to use the sensor to calculate revolutions per minute, and now I can put a motor on this, figure out how to control the motor, and then write the code to do the controlling to set it to certain RPMs.